In this particular slide, we will summarize the key advantages of OFDMA, and you can see from the slide that users bursts are scheduled across both frequency and time in OFDMA. So that's a key advantage. Per bus modulation, coding, and transmit power can be achieved in OFDMA. So each user can be modulated with a particular QAM and particular coding scheme, and also assigned a particular power for the maximum utilization and efficiency of the system. There is much higher granularity in resource allocation, more degree of freedom in scheduling, has an improved fairness, and also quality of higher quality of service. Orthogonality of users are maintained using large symbol duration and cyclic prefix. User concentrate transmit power over partial bandwidth. This is a key concept of subchannels, which actually allows to have much higher cell radius, higher granularity in resource allocation and power control. Inherent advantage of multipath in OFDM, and also we have flexible subchannelization schemes. One of them is called distributed pseudo-random permutation, another is called contiguous permutation, which is called selectivity based permutation, and OFDMA is scalable to different channel sizes. We're on slide number 8, and in this slide the key concept of cyclic prefix is presented. So every data symbol is affixed with a part of a cyclic prefix. So what this helps is to counter the intersymbol interference. So on the right hand side you can see that the data payload is actually prefixed with some part of an cyclic prefix, which is 1/8 of the total symbol time, and this helps in eliminating the intersymbol interferences and retains orthogonality between subcarriers. In OFDMA there are kinds of subcarrier. Some of them are called pilots. There are DC subcarriers, data subcarriers, and also guard subcarriers. Pilots helps in estimating channel, and also is used for tracking users. We are on slide number 9, and in this particular slide the key structure of OFDMA frame is presented. On left on the side you can see that the first symbol of an OFDMA frame is a preamble, and then we have downlink map and uplink map, and then users are allocated data bus. Between downlink and uplink we have a TTG gap, which is called a transmit transition gap, and then we have an uplink bus, which is characterized by 3 symbols of control channels. One of them is CDMA ranging, then we have periodic ranging, then we have ACNAC channels, and then we have CQICH channel. And the TDD frame is actually the frame is TDD, and we can divide the downlink and uplink ratio accordingly as required by the systems. And different permutations for downlink and uplink is supported. So user can be allocated an PUSC zone and AMC zone, or in the uplink we can allocate a PUSC or AMC zone. We can also use STC or MIMO mode. The frame allows to use STC and MIMO modes. Yeah, we will go into deep discussion about PUSC and AMC in coming slides. Essentially, from this particular slide, I wanted to give you a brief structure of the OFDMA frame, and this is a 5 millisecond frame, and in this particular frame there are 3 important things that we need to keep in mind, and one of them is that each frame has initial symbols for control channels. So in the downlink we have preamble and downlink map and uplink map. In the uplink we have CDMA ranging codes, ACNAC and CQICH channel, and then there are burst allocated to users, and these burst uses different kind of permutation zones. The permutation zones are partial use of subchannels or AMC, and we will cover these permutation zones in detail. And in uplink we again have permutation zones for user. Now TDD frame is flexible in assignment, so number of symbols in downlink versus number of single symbols in uplink could be assigned as per the requirement of an operator. So let's say an operator is more interested in internet traffic, so more symbols can be given to downlink part of the frame, and less symbols can be given to the uplink part of the frame. There are total 47 symbols in a 5 millisecond frame. So most common configuration, I am not advocating any configuration, but most common configuration could be 35 symbols in downlink and 12 symbols in uplink. This translates to 75% of the frame in downlink and 25% of the frame in uplink, or maybe a 29 18. This could be like 62% in downlink and 38% in uplink. So it all depends on operator, how would he like to size the TDD zone. In this particular slide, we will understand the key concept between adjacent subcarrier allocation, which is called AMC permutation, and distributed subcarrier allocation, which is called PUSC or FUSC. So let me first tell you, put in front of you that AMC is mostly suited for users which are mostly fixed and nomadic, and PUSC is more suited for users which are highly mobile in nature, or are pedestrian, or this profile suits more for mobility kind of profile. Now in AMC um, the number of subcarriers are adjacent, and it is allocated to a particular user. So you can see in the left hand side that subcarrier allocated to user 1 in a particular time, and then we are having subcarriers allocated to an user 2 in particular time, and one or two are adjacent in and these users are essentially can be benefited in a much better way if they are fixed users. Now in the PUSC part, if you see on the right hand side of the picture, you will see that each user is given a subcarrier in a particular symbol time, and then the next user is given a different set of subcarriers, and the third user is different set of subcarriers, and they are not contiguous in nature. And this kind of permutation allows an frequency diversity to each user, and which can take advantage of diversity schemes, and this helps in counteracting fading, and also improves SNR of user. So both the schemes are having their own advantage and disadvantages. What I found is AMC is more suited for fixed kind of an deployment, and PUSC is more suited for mobile kind of a deployment.